Olveda, I hope I pronounced that right. Anna Olveda serves as the VP of Engineering at Slab-works, where she spearheads the development of innovative and sustainable project solutions for high-performance shallow foundations. With over 10 years of engineering experience, including 2.5 years in her current role, Anna brings extensive expertise in designing and managing projects that emphasize efficiency, reliability, and client satisfaction. Holding a Master of Science in Civil Engineering from Texas A&M University, Anna has a robust foundation in structure design and project management. Her career includes consulting on large-scale structure projects, fostering collaboration with diverse teams, and enhancing operational efficiency through standardized tools and process. At Slab-works, she drives advanced engineering practice to support the company's mission of delivering cutting-edge foundation solutions. Renowned for her leadership, strategic vision, and dedication to excellence. Anna is also passionate about mentoring emerging engineers outside of work. She draws inspiration from gardening, reading, and acquiring new skills, reflecting her commitment to personal growth and community engagement. Welcome, Anna.
Studying today, and if we have any veterans in the audience, happy Veterans Day tomorrow. I appreciate your service. So like she said, my name is Anna Olveda, and I'm here today representing, invited as the forensics group is currently launching on the Texas section side, and I volunteered to help chair the efforts and gather interested engineers from all civil aspects to participate and just speak up on items that you see or feel that can have a refresher or a microscope to kind of look at, is this the most efficient or accurate way of any aspect of civil engineering? So it's just a way to have a conversation, get the ball rolling. And I want to present a case study that was presented to Forensics 2022 Congress from some forensics engineers. And I was told 20 minutes prior to the presentation that I didn't fully capture and convey everything that the forensic engineers were trying to address in their 8-page submission to the Forensics Congress. So I'm going to disclaim this is solely my interpretation of it. Based off of that, we've extended the offer to the authors of this article to provide perhaps their own slides to fully capture what they were conveying in their argument. And so I believe that these conversations are what help push us further to fitness our practice. And so with that mindset, I kind of want to present this in a very neutral aspect and just show A, B, but I really want to focus on us communicating and highlighting certain instances that we can all share and learn as and I apologize, I'm gonna have to switch between two screens. So let me be clear again, today's objective, I'm only here as a neutral presenter and invite everybody to look into the forensics group as we become a lot more involved with the different institutes at the section level offering. So what we're going to dive into today are 5 key areas. First, a very basic understanding or misunderstanding of the technical topics that were presented in the Forensics Congress in 2022. The professional organizations from both PTI and ASCE's response to that, and then We're going to recap some of those fundamental engineering principles that we all learned in school to kind of highlight what these reports are arguing. And again, this is from a structural perspective. However, keep in mind that it's a soil structure interaction. So we can only design so far, which is why we truly want to open the communication to geotechs, give your perspective so that we can, between the both of us, we put two heads together and we make a great solution to some of these concerns. So after we review some of those engineering principles, we're going to track how our thinking has evolved from 2022 to now. And it extends way beyond that because the ASCE residence guidelines was established back in 2002. And this was basically just I call it almost a table of contents of information to find more in-depth design approaches. So this is more of a guide that helps align. Oh, it's
not updated there.
Apologies.
Is this? Okay, do you want to try it?
So now people online can see what we're seeing or vice versa. So then after we kind of see how we've evolved over the course of several decades, we want to find the common ground that exists between the different practices. And finally, identifying opportunities where we can all collaborate in a hopefully non-confrontational location where we can share ideas and push our involvement or growth in the engineering industry. So this matters because many of us face some of these exact challenges in our daily practice, and understanding the full scope of this debate will help you make more informed decisions your day to day. So let's take a quick look at our roadmap for today. What do I need to?
This one.
Okay. Oh, okay. So we're going to open on why, again, I feel this matters, and kind of a consensus of the other engineers that I've spoken to around just different conferences, fundamental principles. Then we'll introduce a technical debate, and kind of dive a little deeper into just more of our practical applications, how we can collaborate as an industry, and things to possibly look forward to as we continue to grow and evolve. And then we'll have a Q&A for any insights, so I encourage you to share some of your thoughts and questions. So let's start why we're all here. So these aren't just abstract numbers on the screen that you see here. $15 billion, that's the annual damage from our expansive soils nationwide. To put that into perspective, that's more annual damage from floods, hurricanes, tornadoes, and earthquakes combined. So here in Texas, we're pretty much the epicenter of our wonderful expansive soils. So 60% of the soils are expansive. And when we look at our Texas map, the darker areas, or it's of the density of kind of the foundation failures that we encounter. It's also overlaid with the number of foundation repair companies that we currently have in the state. So the kind of an indicator of where we're at on this. So they're all various forms of expansive soil, which grade being the most expansive. Sherman is one of the most highest fluctuating soils in our state. So it's a different level of, or different classification of expansive soils. And as for in the profession, every evaluation that we perform carries liability. So every report that we write affects our reputation, and every decision that will impact public trust in our profession. So what I'm about to show you as a community turn disagreement about some of these evaluations into progress. So it's not a story of conflict, it's more of a professional growth. So the next slide was going to talk about basically how the conversation started opening up about shallow foundations and expansive soils. In 2022, a group of engineers, a lot of them based out of Dallas, submitted an abstract paper stating or questioning how we currently have our codes written, and by codes, more design guides from both PTI and MSCE. So there is the question arising from some of these processes is for a global view of the foundation in itself, whereas some of the issues that are more common in our industry are localized failures. So rather than applying both, that's where the confusion comes in, is when do we look at it from a global aspect? And when do we look at actual localized areas of concern? And so PTI has their edge lift and edge drop instances, but then ASE factors in your tilt and your slope. And so when does it become a failure and the homeowner has to invest a lot, several $1,000s into foundation repairs, and when is it acceptable? So having that clear definition placed helps all of us be on the same page regarding the issues or concerns that we're seeing out in the field. So that's a quick recap of where it is. It's perfect. Thank you. Try not to write big. So imagine you're called to evaluate a multi-family complex. You measure a 29-foot long cantilever along the slab edge. Your instrument shows that it's a 2-inch deflection, and the brick veneer has visible cracks. So the homeowner wants to know, is my foundation failing? One engineer uses one design example, and it says, you've exceeded the L over 360, therefore your foundation needs repairs. Another engineer gives a different assessment. It says, well, I'm using PTI and it allows for a 1% slope, and we're well within our means of anticipated movement of this foundation. Therefore, no improvements are necessary. So 2 different designs, 2 different respected engineers, both following their design guides, and there's still a gap in between both assessments. And so that's a little brief overview of what we're taking the dive into. And I am extremely oversimplifying this, but this is some conversations that are occurring at a deeper level. And this is what we're hoping to address in its own lane, localized way.
Is that already defining structural?
So that's kind of, although depending if it's tilt or if it's actual expected or if it's just your, you know what I mean? Like it's L over 360 because that's general, but then International Building Code allows for more stringent L over 600 if you have more fragile or facades or finishes like stucco. So it goes so that it's serviceability to, or most of the time it's serviceability, not necessarily detrimental to. It's just inconvenient because doors aren't shutting, windows ain't closing. And so this is a type of concerns that the homeowner sees. They see, I can't close my window, I can't open this door. That's your serviceability issue. So yeah, so that's when we get the call, and that's when we have to go back out there and say, okay, well, what's going on? So part 1, fundamental principles. So just going to do a quick refresher from our grade mechanics and materials courses, and to establish kind of a ground base of my initial assumption of the 2022 presentation, which is a lot deeper than what I'm presenting here. So just going to jump into the quick basics.
So you need the mouse to be.
Okay. So quick mechanics review. We are, remember, simply supported beam with the uniform distributed load. And then we have a cantilever section when our foundation is actually unsupported around the perimeter. So the question in place that I originally took, which is not the core concern for this presentation, just want to make sure that's completely stated, was L over 12. So that was one of the concerns that was derived based off of, we're going with the first degree or second degree of curvature. So because those assessments or analysis impact how they're designed. So in the building code, it states that for any cantilever members, the length should be taken as twice the length of the cantilever to be able to equal the same amount of movement in a simply supported beam. So, but this has been mostly taken as an elevated slab. It wasn't necessarily directly correlated or applied to a slab on grade foundation. It just spoke in general terms. So, for the cantilever, then it's defining what is that L distance in the deflection ratio, because is it the actual length of the cantilever or is it something else? How do we define where that fixity point is? It's underneath the slab. So we have to use our own engineering judgment of where we start seeing these deformations occur to be able to validate the length, to be able to quantify your cantilever to ensure that it's within reason.
So the cantilever can be any portion of the slab or?
That's unsupported.
Oh, that's unsupported, okay.
Correct. That's on the edge. So that introduces the conversation about curvature. So basic fundamental principles, your curvature, simply supported beam, your deflection passes, cantilever beam. If we use L over 180 or L over 360, it passes. If we use 2L over 360, which is L over 180, then that's when we start seeing a failure. So depending on which book you choose to use that day or what length you enter specifically impacts your decision assessment on your findings of this performance. So for the same curvature, okay, let me backtrack by saying curvature is represented by kappa, which equals your moment over your modulus of elasticity times your moment of inertia, which equals 1 over the radius of the curvature. So for that same curvature, meaning the same strain in the extreme fibers, the same stress, the same potential for damage, a cantilever length must be compared to a simply supported beam equivalent of 2L. So when we look at these diagrams, the mathematics proves that a cantilever with the length has the same maximum moment. And I didn't quantify them, but I can send it to you if you guys are interested. So these principles have become absolutely crucial to understanding the debate that we're going to explore. So this is where we introduce the geotechs, the soil structure interaction, very critical to our success of our designs and forensics review. So now we move apart from the structural mechanics and revisit the real world where structures actually sit on the soil. So the Winkler Springs model, it treats our slab like it's a flexible plate on an elastic spring. So each spring represents the soil subgrade reaction. Q equals K times delta. So when the soil swells or shrinks, those springs push or pull on our slab. This is where our geotechnical colleagues, the experts, become crucial. So they predict the different movements. You characterize spatial variation, and you guys tell the structurals what the soil is going to do, or how it's going to perform, or how it's going to react to our foundation. So here's the key that sometimes gets lost. Structural engineers can't prevent the soil from moving, and we're not designing any rigid monuments. We're designing a movable structure that accommodates that movement as predicted by the soils engineers' assumptions on the soil's movement. So our foundation will deflect It has to deflect. The question isn't whether it's going to move, but how much it's going to move. And then that brings us back to, well, how do we know if it's moving too much? So and then another factor to layer into this roller view is, well, ACI allows for 3/4 inch tolerances in construction. How much of it moved, or how much of it was constructed within this tolerance level, and how much of it moved during the course of its life? Is that factored in? Because that's potentially 1.5 inch movement, or not movement, but variations that was factored in after it was constructed. So how do we distinguish between an imperfection from actual movement? So this is where the technical debate began. This is when smart engineers disagree. So we have a group of forensics engineers who are constantly seeing this every day, and now it becomes a liability of, well, the code says this, will I defend this in court? Will the insurance pay based off of my report? And it opens a conversation of, this is what I'm seeing currently, designing this all day, every day. Let me bring this to a group of board members that represent different professional organizations. We're all volunteers, and everyone has a different view of the microscope. So depending how broad that expands is your exposure to different instances and just different circumstances. So being able to provide your perspective, your viewpoint based off of learned lessons that you have helps contribute, make us a more well-rounded, profession. See, so this is when the smart, experienced engineers kind of look at the same problem and come to completely different conclusions. What happens is what actually helps reshape our organizations. These were, I'm going to kind of skim through these. These were extracts from the Clean Elite Forensics Congress 2022. This is public information, makes it accessible. Anyone can read these reports, and I encourage you to do so. The case, it provides a case study and its measurements, as well as its arguments. So of what they see is not currently represented in current guides. And this was published 2022. So they were referencing the 2018 information that's out there. And I believe in 2024, some of the design guides actually implemented some of their changes. So that's great for us all as awareness, since there might be instances or circumstances that I don't necessarily see, but can be helpful in the future when I do come across that. So it's just help paving that path to have a reference from someone who's experienced it and learned from it to share with the group. We did get a response from both committees. The PTI consisted of 7 committee members. MSCE Texas had 7 committee members. However, 2 of those were on both committees. So you can look at it as, well, there was collaboration to be able to have, I guess, both viewpoints have a well-rounded response approach, just based on interpretation and output. And given that their responses weren't exactly the same, each one gave a different perspective based on their responses to the certain design guides. So I want to kind of touch on that. This comes directly from their responses, citing the code of when it were to look at localized deflection ratios versus incorrect cantilever analysis. So the technical bricks illustrated. Go back to deflection. So again, failed with intolerance. Different repair companies, different repair recommendations can exceed $50,000 in potential repair. So I used the information out there to apply to a real world scenario where you're either the homeowner or representing the homeowner. And this is the results of our findings. So we must have a concern, and this is why we care. This is why we do it. This is why we go through our training to make sure that we're able to provide a solution to the people that we are engineering for. And just a little last note. So again, this is an academic. Now it comes down to, this determines whether someone's refinancing their home to cover these repairs, or whether the insurance is going to approve it, or whether lawsuits are going to be filed. So that's a different motivation as to why we should care and take a closer look. So again, started with the 2022 publication. It kind of caught the design guides off guard because it came out of left field in the aspect that they were unperfect. So 2024, they resubmitted another presentation, and that goes more into your curvature versus deflection. And what we're proposing now is, rather than having more of an attack mode, we want to hear your voices. We don't want it to get to the point where now you're having to argue your thoughts against any publications and you're liable for those decisions. We want to make sure that we are designing the best solution forward without having that extra exposure. We want to ensure that everyone knows that they have a voice they can hear, and we have a specific location where if you don't have an extra 20 hours a month to volunteer for some of these board seats, you're not being ignored or pushed to the side. We want to make sure that, we hear and we learn from each other. And so this is how we evolve and innovate. We encourage the debate, and we encourage any initial controversy that may be viewed as, but the profession doesn't just resolve the debate, it transcends the all new approaches, and it's accessible to all engineers. So the paradigm shift. So in 2024, the Forensics Congress, Kalina returns with co-author with the original co-author and the new author. And so this proposal wasn't arguing, or may have it evolved into measuring the actual causes of damage, which is your curvature. So your radius of curvature, rho, equals EI over M. It directly relates to your strain, stress, and damage potential. So when we think about the shift, instead of arguing about how to measure the deflection, ask a more fundamental question: what actually causes the cracks that we see? And it's not deflection per se, but it's the bending stress, which is directly related to the curvature. This wasn't admitting anyone's right or wrong. It's the evolution. It's taking that lesson from the original discussion and seeing how we can evolve it and grow from it. So, in my opinion, it's emerging at its finest. You are able to learn, adapt, and scale accordingly based off the information that we have. And that's truly what matters in our practice. So why the radius of curvature matters. So when you look at these correlations, let's say you have a brick veneer, it's cracking at a radius of curvature at 750 feet. Your drywall, your tape starts separating at 1,000 feet. Your tile grout, 500 feet, and the doors bind you start feeling that at 400 feet of the curvature. So instead of telling a homeowner, hey, your foundation is failing because it doesn't meet our L over 360 number that we have in our book, we can now say with certainty, your radius of curvature, you can expect 1/2 inch of your brick veneer at approximately a 4-foot spacing. So if you start seeing, okay, well, at 4 feet, I'm actually seeing 2-inch deflection. Well, now let's take a closer look because this is what's expected. If you experience more than that, that's when it should be concerning. So when we put that knowledge together practically, the engineering, that's engineering for the homeowner can understand, but it's also predictive rather than just diagnostic. So we can correlate our measurements directly from observed damage patterns. If the calculations predict brick cracks, but there aren't any, well, then we know something's off with our analysis. So it's a good indicator for both the homeowner and for us, what we're seeing, what we're calculating versus what is actually out there. So practical applications. Now, when we put it all together, theory is important, but you need the tools there that we can all use Monday morning. So let's see how we apply these insights in our practice. So this is simply what I have gathered. This is not a code. This is just best practices from what I've learned that I'm sharing with you all. It could be a tool in your tool belt, or you can disagree with this, which we strongly encourage. So a framework that incorporates everything that we've learned is step 1 is critical. So you have to document your distress always. Pattern mapping and locations. Are we experiencing this type of cracks and failure or cracks and movement throughout the entire foundation, or is it localized in one building corner? Is there a reason why? Is there a tree? Is there water leakage? Is there drain, like your soil's not draining properly? What is causing the distress? Having a full awareness, full scope, taking a full assessment of the entire property to understand how it's impacting the structure. Then measuring the elevations. Well, 2 inches here, 1 inch there. What type of movement are we experiencing or seeing? Analyzing those movements and then correlating that, including based off of our knowledge in design. So some of the best practices that I've experienced or witnessed is common mistakes to avoid. We can't assume that there's a cantilever without fixity. We can't ignore construction tolerances, and we can't use L for cantilever limits. We can't rely solely on the elevations, and we can't skip the stress correlation. So, but we can verify backspan conditions. We can account for that 3/4 inch plus or minus ACI tolerance. It is helpful to have the 2 length for your cantilever assessments. And we should document everything, especially the distress patterns, and applying our relevant engineering judgment to these cases. If I may.
What's meant by skip distress or
Don't skip distress correlation, meaning don't ignore localized areas over a global viewpoint. So distress correlation is, okay, well, this moved 3 inches, my brick ledge is cracking up here. So the correlation between what the soil is doing to the structure. Don't dismiss those distress calls. Just keeping a broad overview, making sure, so get structural perspective. So making sure that your geotech, like you're assuming and ensuring it's not just the structure, it's the soil and the environment around it. So don't disregard those. Don't skip them. So interdisciplinary collaboration. So theory is important, yes, but the tools that we have to use on Monday morning is what sets us apart. It's what helps us grow. It's what also makes us competitive. So seeing how to apply these insights in your practice helps make you a more reliable, trustworthy, knowledgeable engineering in our practice. So tell me. So neither discipline has all the answers. Structural engineers, we understand the load path, we understand stress distribution, we understand deflection limits, but we can't predict how the soil moves. Geotechnical engineers understand soil mechanics, the moisture mitigation, and the volume change potential. So we need to collaborate to be able to translate that information back and forth and apply it to a successful project. The sweet spot, right there where the magic happens, is where we're both in communication and sharing lessons learned to each other. So if we predict, or if you predict 2 inches of differential movement, we can calculate whether the structure can tolerate it. So, okay, well, if we know it's going to move 2 inches, we can increase our moment of inertia to ensure that it's strong enough to resist some of those volumetric changes. And that type of collaboration is what helps build a stronger product. Another example that we observed is stress patterns is when we explain whether the soil conditions could cause specific patterns. So together, we diagnose the root cause. Yeah, the best reports I've seen indicate both prescriptives and then clearly distinguish between those and working in harmony. So kind of where do we go from here? We understand that, we agree, but there's still a little bit of a disconnection, I think, in my opinion. So moving forward, we've come far. However, our journey still isn't over. So let's see what opportunities we have ahead. So in order to, I guess, it's helpful if me and my friends kind of talk in a circle and say, no, we know we shouldn't do this, and we're going to ensure we implement those in our design. But that doesn't necessarily help anyone else other than the people in our circle. So being able to document and share these lessons learned, people can pick and choose their own tools based off of their current projects. And so our propose is to have a database and have a central location where we can include lessons learned, kind of a safe haven. We're not here to judge or critique anybody. We're here just to learn from others, learn from smartest person, and learn from someone else's mistakes instead of recreating it. So yeah, develop that specific environment to be able to have some of these that go outside of the realm of what the current design guides give us, going beyond a prescriptive design method, going a little deeper into variations in some of these assumptions. So priority 1, develop material-specific deflection and curvature criteria, perhaps. Knowing certain material acts or performs a certain way. So building that more defined within our design guides. It not be so general. It's more of a, if you're here, do this. If you're there, do that. Maybe a flow chart. Create predictive models. So imagine telling a client, based on these soil conditions and this foundation design, here's what you can expect in 5 years, in 10 years, in 15 years, which is critical since now the government's talking about expanding mortgages to 50 years. Currently, we have a 10-year warranty on our foundations, so we can guarantee them 10 years it shouldn't fail because it's covered under contractors. But what happens when these 30-year loans now become 50 years? People are in there longer times, larger foundation footprints, bigger building footprints outside of a rectangle, which a lot of this was originated off of. So, and then what we haven't seen very much of is advancing our monitoring systems, being able to have sensors and look at it over the course of a year, 2 year, 5 years, and being able to gauge where it was at the initial construction, what it's going to be now, and kind of how we can see if there's cyclic changes or if it's something completely a no-no to us right now. So we won't know that until we have the data, until we can, but that's future, hopefully in the direction that we're moving to. So we do need field data to make these advances successful. Otherwise, we're observing and reacting to what's currently there rather than predicting or offering more information. So I'm going to leave you with a little bit of wisdom from our founding father. In engineering as another field, progress comes through the resolution of controversy by the light of facts and reason. Tazagi principle. So notice that he didn't say controversy. He said it's resolved with facts and reasons. Oh, wait, I'm sorry. He didn't say avoided. He said it's welcome. We resolve it with truth. So that's exactly what we encourage all engineers to do. And yeah, we examine it with facts, field measurements, distress observations, engineering calculations. We apply the reason, fundamental principles, code requirements, and practical experience. So the result, we're all better engineers because of this debate. So the principles should guide us future challenges. We shouldn't shy away from confrontation or professional disagreement. We should embrace it, examine it, look at it with a clean set of eyes, understand their argument, understand what you understand, and try to fill that gap. So quick summary, key messages, you take away one thing. For our practice, we understand principles, not just procedures. We verify assumptions always, and we correlate those with observations. For our profession, disagreement drives innovation. Our collaboration yields solutions. Everyone's input matters because we all have different experiences, and better engineering serves our entire society. Okay, so kind of where we started, closing thoughts, started with submissions to Forensics Congress. No one's heard of it. I encourage you to check it out. It has a conference every 2 years, even number of years. So we'll have one in 2026 at the national level. Where we are, we've agreed to disagree on certain aspects, depending on process and procedure. Where we're going is hopefully gather all these thoughts, all these experiences, and learn from it. And our journey continues. So I want to thank the GI track to allow the forensics group to have its first presentation to the ASCE members and the Society of American Military Engineers. You guys are encouraged to contribute as well. We are actually having an open submission for any, like the ASCE residence design guides. It's free to everyone. It's on the ASCE Texas website. We're actually opening up the conversation of the topic for anyone to submit anything that they see could benefit from reevaluating or suggestive wording, or maybe highlighting inaccuracies within other codes. Jenny with Texas section will be sending out an email to all ASCE members in the coming weeks with instructions and a form that you can fill out to help automate the system. And it has a March 31st deadline, which we got extended because originally it was December. Doesn't give anyone much time in the holidays. Because we do want to hear from everybody. We do want to see kind of the involvement from when it was last revised, which is quite a while ago. And as a forensics group, we want to make sure you have the tools, resources, verbiage readily available. So we've even considered, okay, we'll submit your concerns. We'll have a ongoing form that we can kind of summarize and produce to the Residential Foundation Committee on your behalf, to make sure that the more we contribute, the more that we can assist. Currently, it is very up and going. So our forensics group is about 1 year old. So we're still doing a lot of the logistics. And so we hope to have our first presentation Q1 of 2026 between January and March. So we'll be sending out emails for that. And yeah. And if you guys don't have questions, discussions, put up a couple discussion topics you may want to talk about or yeah. Any questions? Right. Want to thank AC Dallas again, and yes.
Well, what's the difference between radius and curvature and measuring the deflection? Because you're looking at curvature over a certain distance.
The radius and
And to
curvature
get
is
to
your
the
second
radius,
derivative.
right?
So it's your second derivative. So it's the result of your deflection.
Why wouldn't you go back to work that was done by the Navy Facility Design Gang back in the 1950s, where they looked at roughly 1,000 structures to get deflections for edge lift and sound of the walls, and how to measure the deflection over a certain distance, which would give you effectively a curve.
This was so I'm going to know the history of PTI and MSCE. So PTI was derived, it was formed back in the early 60s, 70s, based off of a square slab that was tested in California. And that's when you have just a simple shape structure. As it's evolved, all we've done is introduce overlapping rectangles. So even on the structural side, we have a lot of empirical limitations. So I agree with you entirely. Even the Army has another publication on shallow foundations that can also be referenced, but we need to collaborate, work together, use the resources that are currently available and suggest those improvements to our current method. I completely agree with, there's a lot of great information already tested and out there. We have and this is where there's a disconnection between the board of individuals on these committees and the design engineers.
The only other question I have, and then I'll shut up. The PGI design in soil protection has actually makes sense. And if you go into the number way back when, you'll find that all that stuff was made up by PTI. So when we analyze its height, we can get PBR. We got 45 people there, we get 40 estimates of PBR. That's okay. But when we go into the PTI design, and we can do all of it, it's illogical and doesn't have any theoretical basis to it at all. So where does that leave us?
So I can speak intelligently on the geotechnical side, which is why I encourage you to become more involved and voice your knowledge with us. I have similar arguments as well. That's why I
Thank you.
I couldn't go use CPI.
again, that's a currently only design guide for if you're using post tension to be able to use their methodology. So that's where we have to open up that conversation and provide more feedback.
Was the example we provided, that building,
Mhm.
what led to this discussion?
That, yes. So it was started.
They spend the money apparently fixing and following engineering instead of attached the settlement or different settlement mistakes that they have led to the cracking was preventing the structure from being habitable. And now we're trying to see whether that really applies or not. Is that what it's coming down to?
I don't know the exact specifics of this case today. I just know that it was submitted as part of the abstract and part of the documents. So it was shared in that aspect and not anything behind it. What I can assume is that it wants to highlight that there's sections beyond your overlapping rectangles, because from a PTI perspective, structural design engineer, we don't take into consideration the true building footprint. We do sections or strips of rectangles. And so if some assumptions were, there's gaps within there in that empirical design. So we need to take a closer look because the cantilever section, although it's there, it's not that that design of the cantilever outside of the main of the structure is not necessarily highlighted in our empirical design. So we're assuming that it's only that one rectangle or a large rectangle, and then there's that gap in between. So those stresses are invisible to the equations.
What kind of structure was it? Still,
A residence.
multi-story?
I cannot tell you. I would have to go back and read the document. I was just looking at the. But I do encourage you to read the article and the argument based off of this. You can. This is the 2022 original publication.
Say 2 inches ahead of it.
Over
Right
here.
on the right, it's like the one, it's 7.
Yeah, edge drop area, center left. I might have just been a typo on my behalf.
You measure it in curvature.
Let me pull up the spreadsheet. I didn't put it in. Curvature. Oops. This is the equation for your curvature. And share with you a design example if you like. A little after the.
You actually measure the curvature and calculate it based on the time moment.
Currently, so for the 2022 publication, there was nothing in the code. And I think it was touched on the 2024 publications. So. And that was introduced by PTI. So that was introduced. Here. The localized deflection ratio. But there's still, I guess, room for improvement on how it's presented, how it's defined, the difference between your deflection and your curvature radius. Thank you, everyone.